Yeah, let me just check. Okay, cool. They're moving. Yeah, so I'm Laura. I'm a final year PhD student at the ICG in Portsmouth, and I'd like to talk about this project that I've done with my supervisors about multi-field alpha-attractor models of inflation, where turning trajectories and geometry play a very important role. So thanks a lot for nicely introducing already what inflation is and why it's motivated, but just for those that were not connected. So the cosmological inflation is a period of accelerated expansion in the early universe, as being proposed initially in the 80s as a theory to solve the main problems related with the hot Big Bang cosmology. And also later it was realized that it really nicely also seeds the large-scale structure of our universe. The best way of describing the curvature perturbation produced during inflation is through statistics. And the first thing you want to look at is the two-point statistic of zeta, also known as the scalar power spectrum. So one of the possible ways to parameterize the scalar power spectrum is through a power law, where here you see AS is the amplitude, then we have a scaling with respect to the CMB scale in this case, and a tilt that is NS minus 1 for the simplest models. So you can see here that if NS is exactly equal to 1, then you have a completely scale invariant power spectrum. So it means the power does not depend on the scale you consider. If NS deviates from 1, you have other type of behaviors. So from large-scale measurements of the cosmic microwave background anisotropies, we have bounds and measurements of the amplitude, the tilt, and of the scalar power spectrum. And from these, we learned that zeta is nearly Gaussian and also nearly scale invariant. We can also derive bounds on primordial gravitational waves that are predicted to have been produced during inflation, and these have not been detected yet, but they are constrained. So basically, what I'm saying is that we know how the scalar power spectrum looks like on large scales, but unfortunately, there are not much constraints on how it should be on smaller scales. So, for example, some models of inflation predict growth of the scalar power spectrum on small scales, for example, with a peak, as in the plot that I'm showing you. And the consequence of having a large peak in the scalar power spectrum is that you can have a large production of second-order gravitational waves, where the energy density is schematically given as an integral of the square of the scalar power spectrum. And also, if p zeta gets to very large values, around 10 to the minus 2, you can also have primordial black holes production. So you can think about these second-order gravitational waves and the primordial black holes as a way of testing inflation on small scales. As I said at the beginning, we are going to focus on alpha-attractor models of inflation. So these are very compelling models that are in accordance with current CMB observations. They provide nice universal prediction for large-scale observables, and they can be embedded in higher energy theories. Naturally, alpha-attractor models are formulated in terms of a complex field, zeta, that lives on the Poincare hyperbolic disk. So the field space curvature in this case is negative and constant, hence this is a hyperbolic field space. And you see that it is inversely proportional on the alpha, which is also in the name of alpha-attractors. We can parameterize the complex field zeta through a modulus and a phase, and we will identify these two as the radial and the angular fields. And then you have your multi-field potential, which is given in terms of zeta and its complex conjugate. Now, you can transform to the canonical radial field phi, and in this way, the kinetic Lagrangian for phi and theta looks like this. So you have a canonical radial field, a non-canonical angular field, with a multi-field potential transformed as well. And in general, the multi-field alpha-attractor action will look like this, with the kinetic Lagrangian as seen before, and the multi-field potential depending on phi and theta. So for the potential that we consider in our work, we looked at the background evolution. So you can see here the profile of the potential that we considered, plotted against the radial field and the angular field. And on top of it, we're representing different background trajectories corresponding to different initial conditions. Inflation starts here, then you roll solely along the radial direction, then there is a turn in field space, and you experience a motion also in the angular direction, and then some complex behavior, and inflation ends here. So these models, we have shown that these models support turning trajectories in field space. Then we have looked at the effect of the geometry. In particular, as I said before, the field space curvature is inversely proportional on alpha. So turning down alpha means looking at field spaces with a stronger and stronger curvature. So when you move from alpha 0.1 to 0.01 to almost 10 to the minus 3, something changes in the scalar power spectrum. So here you can see the results plotted against K, and moving from the yellow to the orange to the green curves, you see that there is a peak, and the peak can be higher and higher in amplitude. And this peak is produced by multi-field effects. In particular, in two-field inflation, there are two types of curvature: the curvature of perturbation, the curvature perturbation and the isocurvature perturbations, and those are coupled together. In the super horizon regime, the effective squared mass of the isocurvature perturbation depends on the field space curvature. So if here you have something huge and negative, this means that the square mass of the isocurvature perturbation is negative. The isocurvature perturbation gets amplified, it grows tachyonic through a tachyonic instability, and through the coupling that I have shown you before, gets transferred to the curvature perturbation. So this explains why you see a peak in the scalar perturbation here in the scalar power spectrum, and the origin of this peak. So we have compared our models prediction with the cosmic microwave background bounds, and we have found that the strangest bound comes from the tilt. In particular, for models that are compatible with CMB measurements, the peak in the scalar power spectrum has to be at scales larger than 10 to the 18 inverse megaparsecs. And this is very important and strong consequences for the small-scale phenomenology of these models. In particular, the primordial black holes that could be possibly produced within this model must have evaporated by today, and the second-order gravitational waves accompanying a large peak in the scalar power spectrum peak at ultra-high frequencies. Okay, so this is the main result of our paper. And if we give a look indeed to the second order gravitational waves produced within these models, we see the signal here plotted in green, together with the sensitivity curves of space and Earth-based gravitational waves observatories. And you see that for a model that is indeed compatible with the CMB, the peak is at ultra-high frequency, beyond the reach of planned gravitational waves observatories. So for interest, for the ultra-high frequency gravitational wave community. So we have considered multi-field alpha-attractor models of inflation, and we have considered models that lead to enhanced scalar power spectrum on small scales. We have found that the reason for the enhancement of the scalar power spectrum is that the hyperbolic field space is strongly curved And this combined with turning trajectories explains the growth, causes the growth of the scalar power spectrum on small scales. We have compared our models with the cosmic microwave background measurements, in particular of the tilt of the scalar power spectrum. And we have found that for models that are compatible with the CMB, the peak is located at scales higher than 10 to the 18 inverse megaparsecs. The primordial black holes possibly produced are lighter than 10 to the 8 grams. And the second order gravitational wave accompanying the primordial black holes peak at ultra high frequencies. In the interest of time, I've glossed over a lot of details of the work that we have done and other stuff that we have looked at. So please give a look to it if you're interested. And thanks a lot for your attention.
Cool. Okay, thank you very much. We have one question in the Q&A. Are these predictions experimentally distinguishable from other models of inflation?
Okay, I'd say that so on large scales, this the scalar power spectrum looks. Oh, sorry, I can't move the slides again. Okay, yeah, here. Yeah, okay. So you see here on large scales where you do your CMB measurements, the scalar power spectrum looks almost scale invariant, exactly as a single field model would produce. The behavior is very much different on small scales. So I'd say that, yeah, the interesting features of these models are that they deviate on small scales from the behavior, from the usual almost scale invariant behavior.
Thank you very much.